Good morning, everyone. I'm Safa Minat from the University of Rouen, Normandy, and I'm glad to be here to present my research work entitled Merging and Validating Health Ontologies, a framework for ontological integration and evaluation. This work has been done in collaboration with Lina Swalmia and Saeed Abdedin. So, as we all know, ontologies play a crucial role in representing, structuring, and organizing knowledge. However, having these ontologies as a separate resources would be less benefit for healthcare specialists in their work. So we need to ensure interoperability between these resources and creating links to integrate them. In addition, with the abundance of the biomedical data, the analysis and the exploitation of these resources become more and more complex because of the great number of the ontologies and the large number of their concepts. So we can say that there is a real lack of a unified resource that can integrate and harmonize all these existing ontology so that we can use them in our research work. So here we are proposing a framework that can integrate multiple ontologies in the same resource. Specifically, we are focusing on this use case where we wanted to create or propose new relationships. For example, between the concept disease from the disease ontology, we want to propose the semantic relationship has a symptom with a concept symptom from the symptom ontology. The same thing with a concept disease with a concept drug, with the has-drug relation. And for each concept drug, we want to propose has-side effects relations with all the side effects related to this drug. So to do that, we propose to use the sentence transformer models. So these models are basically transformer models that embed textual data into vectors. And we have principally two types of architectures. We have the bioencoders, or what we call the Siamese architecture, and the cross-encoder architecture. The main difference between these two architectures is in the way they process the textual input. So for this one, we embed the textual data into a vector using, for example, a BERT model. And then we calculate the cosine similarity between these two textual data. And for the cross-encoder architecture, we process the input concatenated to produce a score that will be the similarity between these two texts. But as you know, fine-tuning these type of models require a supervised data, which is rarely available, especially in our biomedical domain. So that's why we are proposing a new Siamese or bioencoder neural models that optimize self-supervised data. So here we propose to use the multiple negative ranking loss function that only need the two texts at the input without the label, that is the score of the similarity. And to train our model, we use articles from the PubMed database. So for example, in the PubMed database, we have the title of the article, we have the abstract, and here we have this list of items where we can find the mesh terms. The mesh terms are the categories that we can use them to classify a scientific article in PubMed. So we use the titles, abstract, and these mesh terms to train our models. So we proposed what we call the BioS transformers. These are Siamese or transformer models trained on the biomedical data. And you have to know that for training these type of models, we need to have a text of similar lengths at the input. However, in our case, since we have titles and abstract, and then we have the mesh terms, so we don't have the similar lengths for the input. So we proposed to use these texts of different lengths in input, and we trained the model on these couples, the text for the title or abstract and the term for the mesh terms. And we trained the models. Now we use these models to to embed the textual data from the ontologies to be able to propose the relationships between the concepts. We proposed several variants for these models. For example, here, as I showed you, there is a BERT model, but in our case, we use BioBERT or BioClinical BERT or PubMed BERT, any transformer we can use here. And this one, it gives the best results. That's why we called our model as BioClinical BERT, and we use it in this case. We are focusing on enriching or integrating the ontologies from the pre-DBOntol. Pre-DBOntol is the project where my thesis was held. So it's the predicting clinical diagnoses using biomedical ontologies and language models. And in this project, we aim to predict diagnostic for patients and propose drugs. That's why we are focusing on these ontologies: drug, symptom, disease, and the side effects. So this is our framework that we propose to integrate these ontologies. The first step is the extraction of textual data from the different ontologies. We extracted labels, synonyms, definitions from each concept of each ontology, and then we embed all these textual data using BioS transformers. And then using these embeddings, we create the relationships between all these concepts, and we put them in this unified resource that we generate at the end. And then we also developed an extractor for side effects that use side effects of drugs from the database OpenFDA. And then the next step was to validate this resource that we created using Protégé to ensure logical consistency and that there is no error when we generated this resource. And then we published our resource at BioPortal so researchers can use it. We have generated about 8,000 relation of health symptom, 3,000 for health drug, and 41,000 health side effect relation. Here I put it some examples of the drugs, the relations that we proposed. And you have to know that all these relations that we created here was already validated in our previous work using external resources, and we also solicited healthcare specialists to manually validate these relations. Now this is a portion of the resource that we created. We can see all concepts from the different ontologies with these different colors. So the blue for the disease, symptoms with the red, and side effects with orange, and the rest is the drug. And here there's all a relation that we propose between the different concepts. Finally, to conclude, in this work, we proposed a framework that integrates and validates biomedical ontologies. To do that, we leveraged our neural model called S bioclinical BERT. This model is the sentence transformer model that we trained on biomedical data extracted from the PubMed database using text, abstract, and mesh terms. You have to know also that the BioS transformer or the bioencoder transformer has the advantage that can pre-calculate the embeddings, so we can use them after. That's why it is appropriate for in the case where we have large ontologies with large concepts. So it can handle these ontologies rapidly. And then we validated our resource using Protégé to ensure consistency. And all these new relationships that we proposed in this work can help healthcare specialists enhancing knowledge integration and accessibility. Now, in future work, we want to enhance our merging process using more techniques, for example, using the structural hierarchy of the ontologies rather than just the entities' sexual data. And we also wanted to include more ontologies in our process, such as, for example, UMLS vocabularies. Thank you all for your attention, and I will be glad to respond to your questions.
Hi, you mentioned that you're using ELK, then the ELK reasoner to reason then the final thing and see if the whole structure is valid. Yeah. So what are you doing if it says no, it's not valid? So are you going back to the model and refine, or how do you handle this then if it's not consistent?
Yes, actually, when we created the final ontology, we just imported all the ontology that we used, and then we added the relation that we created. So we wanted to ensure that this step didn't generate any errors. That's why we passed by ULK. But yeah, maybe if there is an error, we will search for another way how to put these relationships into the ontologies. Okay, so if you are interested, there is this special track on semantic interoperability of biomedical data that would be held in the CBMS symposium in Madrid, Spain. So if you are interested, you can send your papers March 7th. I know it's a little bit short, but you can try. So this special track is organizing with Lina Swalmia from our university, Jose Emilio Laura from University of Oviedo, and also Christian Zerpens from Karlsruhe University from Germany. That's all.